So we are now going to continue on with our building of the fundamentals that we need for statistics. So we're going to continue with that sanding the floor, painting the fence, wax on and wax off training that we've been doing, all in service of getting to that final stage where we can do the really cool stuff where we use statistics to make psychology powerful, to take psychology from something that would be reserved only for the rich, only for a small portion of the world who could afford a personal psychologist, and we take it away from the sample and we can extrapolate and intelligently generalize to a population, making psychology available for everybody. So we're getting there, and today we're going to continue to build that skill, and we're going to see that this is one of the first times where we're going to string together a number of different things. So the practice you put in calculating the mean, the practice you put into calculating the standard deviation, all of that is going to come together now, because the more automatic those are, the more straightforward a z-score is going to be. All right, so let's set up z-scores with an example here. So let's say that you're a clinical psychologist. Specifically, you deal with children, and a parent brings in their child and says that their child seems to be having some behavioral issues. Their child is very active, super active all the time, just bouncing off the walls, bouncing off the couch, can't sit still, very, very active all the time. And in addition to that, when you finally can get them to sit still, they have a hard time paying attention. So they can't attend to their homework, they're easily distracted, they have a hard time focusing. So there are two issues that you need to deal with. You need to deal with the activity level, and then you also need to deal with the attention issues. And as a psychologist, oftentimes, what you want to do is you want to treat one problem at a time. It's often very counterproductive to try to treat more than one problem at a time. It's like people who make 10 New Year's resolutions, right? They never do all 10. They're lucky if they don't lose sight of everything. But people who make one resolution, make one promise that they're going to change one thing, those are usually the people that are successful. So in this situation, you would want to assess this child to see what is the bigger issue, what is the greater problem. You want to compare their activity level to their inability to attend. But notice that those are two different things. You are metaphorically trying to compare apples to oranges. So how do you compare activity level to lack of attention? One way that you can do that is through what we're going to do today, which is z-scores. So z-scores, we'll take a look at just basically what they are, the idea behind z-scores. We're going to take a look at how to calculate z-scores. What's the formula for calculating a z-score? What are the properties that these magical scores have because of their calculation and structure? And ways to use it, how to go from an X raw score to a z-score, and then from a z-score back to a raw score. How to make standardized distributions, tons of things that you can do with z-scores, and we'll see also how to calculate these in Excel as well. All right, so introduction to z-scores. So imagine that you are dealing with this child. So you're assessing this child, and it's the first session, and you just need to assess their how bad, how extreme are their behavioral issues. So let's say that you came up with a test to measure a child's activity level, and this is called the active Q. So it's like IQ, it's like the intelligent quotient, but this is the activity quotient. It's a test called the active Q. And let's say that your child's name is Jimmy, and you give Jimmy the active Q, and Jimmy scores 80 on the active Q. That's their score, 80. The question is, does Jimmy actually have a high active Q? Right? Is that a high score? Is 80 something that you should be alarmed at, going, whoa, that's high? Or does he actually have a low active Q? Is 80 a particularly low score, where you would then question the parent and say, why do you think your child is active? Your child is very inactive. The point here is that we have no idea what 80 means. 80 in this context, the number is meaningless. It could be a high active Q, it could be a low active Q. it's completely meaningless until we can put it into context, until we can figure out where Jimmy is compared to other children his age. So if this is the distribution for active Q scores in the population, so if this is the frequency distribution for active Q scores in the population, and Jimmy scores an 80, well then we can easily see that Jimmy has quite a high active Q score. 80's high, right? Most people are in this area here. Most people score below what Jimmy scored. Jimmy has a high active Q. On the other hand, if this is the frequency distribution, so we change the x-axis over here, if this was the frequency distribution of active Q scores in the population, then you can see that Jimmy actually has a very low active Q. And we would need to try to get Jimmy to be more active, not less active. And we would also try to ask his parents and try to figure out, why do you think he's so overactive? Your child's actually inactive. But notice that that score of 80 can have completely different meanings depending upon where in the distribution Jimmy actually is. So we need some way of taking a score and letting people know, where is that score compared to the general population? Is it a high score like this, or is it a low score like that? And we need a way that supplements that original raw score, because 80 on its own doesn't tell us anything. All right, so that's his active Q, and his score of 80 is 25 points above the mean. So we now know that Jimmy has a high active Q. He is much more active than your average child. So then suppose that I give Jimmy the next test, which is the ADHD Q. So this assesses Jimmy's attention, right? So this is his ADHD quotient test. And let's say that we give him that test, and Jimmy's active Q is shown right there. So let's take away the distribution real quick. So that's his active Q right there. We give him his ADHD Q, and let's say that that's his score right here. So he's got an 80 on the active Q, he's got a 70 on the ADHD Q, and now our question is, which one of these is more extreme? So is Jimmy more extreme in his level of activity, or is he more extreme in his level of attention deficit? And notice that intuitively, we would take a look at this and we would say, well, his active Q is 80, his ADHD Q is 70. You know, elementary school math tells us that 80 is bigger than 70, so the active Q must be the bigger issue. The active Q must be the more extreme score. But that is not the case, and that cannot be determined because those are two different scales. That is literally apples and oranges. So we need a way of, again, putting them into a similar context. Because if that is the distribution for ADHD Q, and I'll put the two side by side, so here we have the distribution, the population distribution for ADHD Q. Here we have the population distribution for active Q. In both cases, Jimmy is above average. But notice for ADHD Q, Jimmy has one of the most extreme cases in the entire population for attention deficit. He is literally at the top of the extreme scores on attention deficit. He's high in activity Q, but nowhere near the top. So even though his ADHD Q score is a 70, which is less than 80, in reality, his ADHD Q score is way higher. That is a way more extreme issue. And as a psychologist, we need to be able to identify that to say, okay, this is the more extreme issue. This is what we work on first. This is the key thing that we should tackle to begin with. All right, so in order to understand scores, what they actually mean, in order to compare scores, things that psychologists have to do all the time, what we need to do is we need to describe them with respect to a distribution. Because notice that we could compare the 70 to the 80 only after we put it in the context of the population, only after we put it into the context of that distribution. And those two criteria, those two moves, are what we do when we calculate z-scores. All right, so that's what we're trying to do today. How do we actually do them? What are z-scores? Well, z-scores, they're nothing more than a fancy name for transforming your raw scores in a specific way. So there's a specific way of transforming raw scores. So if you have a series of raw scores here, the same way that you can change US dollars into Canadian dollars, the same way that you can change US dollars into euros, you can change raw scores into Z scores. It's just literally an exchange, it's literally a transformation. And if we had these raw scores here, we could transform them into Z scores over here. And you can see that every raw score of 8 in this situation gets transformed into a Z score of 0.19. So this 8 gets transformed into a Z-score of 0.19. This 8 gets transformed into a Z-score of 0.19. Every 11 gets transformed into a Z-score of 1.33. So this one as well, 1.33. So it's a transformation, but it's a very special transformation because it does very helpful things. So one of the things that it does is it moves your distribution, and it either stretches it if it's too narrow, or it squeezes it if it's too wide, and it does that in a very specific way. So what it does visually, if you have this distribution right here, which is the one that we're taking a look at, so that's the distribution that we just had, that distribution has a certain mean. The mean of that distribution is right there. If you transform those scores into Z-scores, what you do is you take that distribution and you move it and you squeeze it. So you move it so that the new mean is 0. So the mean of every set of Z-scores is always going to be 0, because that's what a Z-score does. It takes your distribution and it moves it to a place so that the mean is now 0. And then the other thing that it does is if your distribution is too wide, it squeezes it so that your standard deviation for your Z-score distribution is equal to 1. If your raw scores are too narrow, it'll stretch it out so that the Z-score standard deviation is 1. So that's what the transformation does. It moves your entire distribution so that the new mean is 0, and then it stretches it or squeezes it so that the new standard deviation is equal to 1. And you can do this for every single set of raw scores out there. So if you have raw scores that look like this distribution here, they're going to have a mean, they're going to have a certain standard deviation, a certain spread, and a Z-score will take that mean and transform those scores so the new mean is equal to 0 and the new standard deviation is equal to 1. And if you have a distribution that looks like this, it'll have a mean, you can calculate the balance point, and a Z-score, if you transform those scores into Z-scores, you will move that distribution so that it has a mean of 0, and you will squeeze it in this case so it has a standard deviation of 1. And it doesn't matter what your distribution looks like, every single set of raw scores will have a mean, every single set of raw scores will have a standard deviation. Your Z-score takes those raw scores, moves them so that the new mean is equal to 0, and your standard deviation is equal to 1. All right, so that's what a Z-score does. So because of this move, because it moves the mean to have a mean of 0, and it stretches or squeezes the distribution so it has a standard deviation of 1, every single Z-score by itself, just the Z-score, will tell you the location of the corresponding raw score in its distribution. So a Z-score consists of 2 parts that allow you to do this. The first part is the sign. And the sign, if it's positive, means that your raw score is above the mean. If your sign is negative, it means that your raw score is below the mean. So if we look at these scores over here, right, these raw X scores, these raw scores, if I was to ask you, is 8 above or below the mean? You have no way of knowing. You have no way of telling. If I was to ask you, is 6 above or below the mean? You wouldn't be able to tell that until you calculated the mean and you did some extra math. On the other hand, though, if you have the Z-scores, you know immediately. So if I ask you, is 8 above the mean? If you have the Z-scores here, you know immediately, yep, positive Z-score, 8 is above the mean. Negative z-score, 7 is below the mean. Positive z-score, 11 is above the mean. Negative z-score, 6 is below the mean. So you know immediately whether your z-score is above or below the mean. If it's positive, it's above the mean because the mean is 0. If it's negative, it's below the mean because the mean is 0. And then the other part of the z-score is the actual number. So you have the sign, lets you know if it's above the mean or it's below the mean. And then you have the number, and the number tells you how far away your z-score is from the mean in terms of standard deviation steps. So because the standard deviation is 1, if your z-score is positive 1, you are above the mean by 1 standard deviation. If your z-score is positive 2, you are above the mean by 2 standard deviations. So immediately I know where a score of 11 is. 11 is above the mean, and it's 1.33 steps above the mean. I know where 6 is. 6 is below the mean, and it's about half a standard deviation, 0.57 standard deviations below the mean. So not only does it tell you whether it's above or below the mean, but it also tells you how many standard deviation steps you are above or below the mean. All right, any questions so far on sort of the background of the z-scores? All right. So how do we get these wonderful scores? How do we calculate these super useful tools? Well, the formula for transforming z-scores raw scores into a z-score, if you're dealing with a population or you're dealing with a sample, they're basically the same formula, basically the same idea. A z-score is going to equal your raw score minus your population mean. So if you're dealing with population raw scores, your z-score is going to equal your raw score minus your population mean, and then all of that divided by your population standard deviation. So what this does, just to kind of give you a sort of conceptual understanding of it, the top part there, the numerator, you might recognize that as deviation. So remember last time when we were talking about variability, raw score minus the mean, that gives you your deviation. So this is the deviation of the raw score from the mean. That's how far away the raw score is from the mean. And then what a z-score does to finish its calculation is it standardizes this by dividing it by the standard deviation. So you have your deviation, you divided it by your standard deviation, and that gives you the number of steps in deviations. That's what makes a z-score so incredibly useful. So that's what it looks like for a population. If you're dealing with a sample, which is what you will mostly be dealing with, same exact structure, we just have to use the sample statistics. So a z-score equals your raw score minus the mean of your sample. So once again, deviation divided by the standard deviation of a sample, standard deviation. All right, so that's the formula. We're going to be using that formula later on in class in Excel, but this is a perfect example of why the exam is open book, open everything, open resources, because you will not be surprised when I ask you to calculate z-scores on the exam. And I'll be honest with you, I never memorized the formula for z-scores after you've done them time and time and time again, because they are very useful in psychology. So you will, in your career as a psychologist, use z-scores over and over and over again. One day you'll just wake up and you won't have to look it up in the textbook anymore. You'll just be like, oh, z-score formula, this is what it is. So don't feel like you really need to memorize anything for this class. It's better to try to understand and just know the steps of what to do. But if you're in doubt, definitely, and I'm kind of beating a dead horse here a little bit because it is your first exam. If you're in doubt, write it down somewhere, write the steps out, and then during the exam, just know where to look, know where in your notebook you have these formulas, and just offload all that work onto the page, and then use your mind for the higher stuff that it was made for. All right, so that's a calculation of z-scores. We looked at the characteristics and the calculations. So just a few more properties of z-scores just to hammer this home. So why are they useful? They're useful because each and every single z-score tells you where your score is with respect to its distribution. It gives you the location of the score. So you know if it's high, you know if it's low. You can interpret the score because it's built in comparison to the distribution. And because of this, your z-scores can be compared to any other z-scores to know which one of your scores is bigger or smaller, higher or lower, compared to its own distribution. And this is how you can change, how you can compare apples to oranges. You take your apples and you turn them into z-scores. You take your oranges, you turn them into z-scores, and then it's very easy to compare z-scores to z-scores. So to give you an example of this, let's say that you are a school psychologist, and let's say that we'll keep on with Jimmy. Let's say that Jimmy comes into your office one day and says, you know, I don't really know. I want to know where my skills are. I want to know what my aptitudes are. You know, I'm thinking about my future career, and I want to know where are my skills. What am I really good at? So you pull up his academic records, and you take a look at his scores from math class up here, and you take a look at his scores from English class. So this is his class's distribution of scores on a recent English test. This is his class's distribution of scores on a recent math test. And let's say that you look up Jimmy's score, and Jimmy got 7 on the math test, and Jimmy got 7 on the English test. So intuitively, again, we might say to ourselves, well, 7 is the same as 7, right? You got 7 on the math test, 7 on the English test. No way of knowing which one Jimmy is better at. However, that's comparing apples to oranges. We need to transform those apples into z-scores and transform the oranges into z-scores. So if you take the raw scores for the math test and transform them into z-scores, that 7 becomes a minus about 0.1. So that score of 7 is actually below average. Jimmy has a below average score on his math test. That score of 7 in English, on the other hand, transforms into a z-score of about 1.5. Jimmy's actually above average, 1.5 standard deviations above average on his English test. So now we can compare those two scores and get real insight and know that for Jimmy's, in terms of Jimmy's skills, he is much more skilled in English than he is at math. And we can compare those numbers intelligently and come up with that useful information. All right, so z-scores are transformed scores. So just one more time, what kind of properties do they have? This one we haven't mentioned yet. The shape. Z-scores preserve the shape of your distribution. So other than squeezing it or stretching it, it will preserve the general shape of the distribution. So if your distribution has 2 peaks, your z-scores will have 2 peaks. If your distribution only has 1 peak, your z-score will have 1 peak. If your distribution is symmetrical, your z-scores will be symmetrical. If your distribution was skewed, your z-scores will be skewed. It maintains the general shape outside of a stretching or a squeezing of your original distribution. Other properties, mean z-scores, the distributions always have a mean of 0. Always, always, always. When you take your entire set of transformed scores and you take their mean, you should get a mean of 0. That's just a property of z-scores. So they always have a mean of 0. Always is going to be the case. And that is because each z-score is sized according to the deviations. And remember that when you add up all the deviations, you always get 0. So because of this, when you add up all the z-scores, you will always get 0. And then 0 divided by whatever number is still going to be 0. So your z-score distribution always has a mean of 0. And then the last property that they have is that your z-score standard deviation will always be equal to 1. Z-score distributions always have a standard deviation of 1, and that is because you are taking the deviations, which are used to calculate the standard deviation, and you're literally dividing all of them by 1. and something divided by itself will always give you 1. So that's why the standard deviation for z-scores always has a standard deviation equal to 1. All right, last thing we're going to do before we take a look at how to actually calculate z-scores. Sometimes you want to go in the reverse. So we took a look at how to start with raw scores and then calculate z-scores. Occasionally you want to go backwards. You want to take a z-score and calculate a raw score. So you might be talking to people who aren't statisticians, and you've done all this work with the z-scores trying to figure out their son's abilities in math, abilities in English, activity quotient, ADHD quotient. But let's say that they only understand percentages, right? They only understand, is he getting 80%, 90% on a math test? So you might need to take those z-scores and transform them back into the raw scores. So that is pretty simple enough to do when you're starting with a z-score and you're trying to recover a raw score. So really you just take the equation that you have for z-scores and you solve for the raw score. And if you solve for the raw score, you will see that the raw score equals the mean of your distribution plus your z-score multiplied by the standard deviation. So a raw score, if you're trying to recover a raw score, you're starting with a z-score, you get the mean of the distribution, you get the z-score, you get the standard deviation of the distribution, and your raw score equals the mean plus the z-score times the standard deviation. And again, make sure you're doing those order of operations in the order they should be done. All right, so that's one way, that's a way to get the original scores from your z-scores. But sometimes you want to go a step further and you want to come up with more intuitively understood scores. And these are oftentimes used and called standardized scores. So standardized scores or standardized distributions are distributions where you yourself, for some reason, pick a mean and pick a standard deviation, and you transform these z-scores so that the new distribution, the standardized distribution, has that mean and has that standard deviation. So for example, IQ scores are one of the most famous standardized distributions because whatever score you get on an IQ test, they transform that so that it is in the distribution that has a mean of 100 and a standard deviation of 15. And if I actually came up with an active Q scale and I came up with an ADHD Q scale, because of the number of people that understand IQ, I would transform my ADHD Q test scores, for example, into standardized scores that had a mean of 100 and a standard deviation of 15, because that would just be easier for the average person to understand. So for those standardized distributions, what you want to do when you're creating it, there's 2 steps. The first thing is you take your raw scores and you transform them into z-scores. So you start off with a set of raw scores and you take those raw scores and you transform them into z-scores, have a mean of 0, standard deviation of 1. So we've already seen that. The next step though is the important one. What you do next is you take those z-scores and you transform them into new scores. You transform them into new values. And this is the important part not to forget. They're going to have a specific mean and a specific standard deviation. And you need to be told, or you need to decide, what is that mean going to be and what is that standard deviation going to be? Somebody has to tell you, make me a new distribution out of these z-scores, and I want a mean of 100, and I want a standard deviation of 15. And then somebody else might come in and say, make me a new distribution out of those z-scores, but I want a mean of 42, and I want a standard deviation of 18.5. You need to be told what is the new mean and what is the new standard deviation. And then once you have those, use the formula for going from a raw score to a, going from a z-score to a raw score. And if you have a mean of 30, for example, and a standard deviation of 10, you would take your z-scores, transform them into a new distribution that has a mean of 30 and a standard deviation equal to 10. So that is the standardized distribution. So we've been talking about this for long enough. Let's now actually do this live in class. So you have this Excel sheet in Canvas, in the practice Excel sheet. So if you haven't already, log into Canvas and let's open that up and get that going. And we will see how to calculate these z-scores using Excel. And I will show you one particular method that is a pretty straightforward method, a pretty useful method. If you would like to do it, there's other ways to do it. Excel always has basically a ton of options on how to actually do particular scores. So if you find another way, feel free, absolutely. But I do want to show you one very easy way to do z-scores and set it all up. All right, so while everybody's getting their Excel sheets open, I'm going to show you the first thing that you do not want to do, and then we're going to see how to work around it. So what we need for a z-score, we're calculating z-scores here. So we have our raw scores. There's our raw scores right there. And we're dealing with a sample, right? So question 1, given the following sample of 10 scores. For each individual score, calculate the following. We want to calculate z-scores. So we saw today that the formula for a z-score is the raw score minus the mean, all of that divided by the standard deviation. So that's what we're going to want to do. We're going to want to set up Excel so that we can calculate the raw score minus the mean divided by the standard deviation. So we might say to ourselves, all right, well, let's go down here and we'll calculate the mean and we'll calculate the standard deviation of these scores. So equals average, open parentheses, highlight your scores. We see that we have an average of 15.2 equals STDEV for sample standard deviation, so no dot P, so equals STDEV, highlight those scores, close your parentheses, and there we have our standard deviation. And then, this is the wrong way to do it. I'll just show you this so that you see what happens. You might say to yourself, all right, now I'm going to do that formula. In the formula, you are going to need parentheses because we need to do that top part first. We need to do the numerator first, then we can move on to what's on the denominator. So we need our raw score, so we can highlight the raw score, minus our mean, and then all of that divided by the standard deviation. We hit enter. We see that we have a z-score of 1.75. We pop that into our answer cell. And we scroll down and we see that we have that one correct. So we've done the z-score once. We definitely want to do this. We want to do the same thing for all 10 scores. So we might think that we can just copy and paste this all the way down. So we start copying and pasting it, and immediately things just go haywire. Things went really wrong really fast, and Excel is giving us this warning, this error message saying hashtag div by 0, meaning that you're asking me to divide by 0. That's something I just cannot do. So what went wrong? Well, what went wrong is that we set up our formulas wrong. So you'll notice that if we double click on this first formula over here, the colors here will let you know which cells are being accessed to calculate this formula. So we're accessing the X score, the raw score, that's great. We're accessing the mean, that's exactly what we want. We're accessing the standard deviation, perfect. And that's why this particular score worked. However, when we went down here to the second one, notice that we moved down one row, and Excel moved down everything one row as well. We moved the formula down one row, Excel moved the formula down, and the cell that it's accessing down one row. So now we have our raw score minus the standard deviation, and then all of that divided by a blank cell. And Excel can't do that. It can't divide by 0. So something went wrong, something didn't work because we set this up incorrectly. Now what we don't want to do is we do not want to have to enter in the same formula 10 times, because eventually you're going to be dealing with 100, 200, 500 scores in your career, and we want to be able to use Excel for the maximal gains. So how do we do this? Well, one way that I'm going to show you, which is a very straightforward way, is what I like to call parallel structure and what I like to call the cascading waterfall of formulas. So what we're going to do is we're going to set up a column of means. So we're going to label this M for sample mean, and we're going to set up a column of standard deviations, and we're going to label that S for sample standard deviations. So what we want to do is we want to calculate the mean for these scores. And what we can't do, so don't do this yet, but what we can't do is just calculate the average and then highlight the cells there, and you'll notice we'll get the correct average here. But then as soon as we try to copy and paste that, notice once again, that average has changed. That mean has changed. Because once we start moving our formula down, Excel starts moving down all the numbers that it's accessing. So we definitely want to calculate the mean, but we can't do it like that. We need a full column of the same number. We need a full column of means. So what we do, and this is the move, you make that top row equal to the mean. So we've calculated the mean down below the raw scores. You want to make that top row in your mean column equal to the mean that you calculated. So that's step number one, using the equals function. Make the mean, make that top row equal to the mean of your scores. And then step two is where the cascading waterfall comes in. Make your second row equal to your top row. So you make row number 2 equal to row number 1. And then you hit enter, and you can see that now we have the correct mean in row number 2. So why does this work? Because now we can copy and paste that second row all the way down. Because this formula here is literally saying, take the row that you're in and make it equal to the row above. And in this case, it's make row 2 equal to row 1. But if we copy that down, we are now telling Excel, make row 3 equal to row 2. And row 2 is being said, make row 2 equal to row 1. So now row 3 is equal to row 1. And then if we copy and paste that down again, make row 4 equal to row 3, which is equal to row 2, which is equal to row 1, which is where our mean is. So now we can take that and we can copy it down the whole way, and we have very quickly been able to make an entire column full with the correct calculation of the mean. All right, has everybody got that first column set up? All right, so not surprisingly, next thing we're going to want to do, same exact thing for the standard deviation. So we've already calculated a standard deviation right down here. So for row number 1, we can pop it in there using the equals function. And then this is the key move. Do not forget this move. Row number 2 is made equal to row number 1. So row number 1 has the number that you want in it. You make it equal to whatever value you need, in this case, the standard deviation. Row number 2 is equal to row number 1. And then that is the row that you copy all the way down to make that column of standard deviations. All right, so we still don't have any z-scores, but what we now have is we have a column of raw scores, our x scores. We have a column of sample means. We have a column of sample standard deviations. And notice that now the information that we need for our z-score formula is in every single row, right? Every single row has a raw score. Every single row has a mean. Every single row has a standard deviation. And this is what I call parallel structure. We have 3 columns that are all structured the same way, structured with the information that we need. So now we can take our z-scores and we can use this formula, and we will say equals, open parentheses, take the raw score, subtract from it the mean, close those parentheses, that's your deviation, and then divide by the standard deviation. And now we have our z-score. So one more time, I'll show you equals, open parentheses, your score minus your sample mean, close those parentheses, and occasionally now, depending upon how wide your columns are, you're not going to be able to use a mouse click to get to the standard deviation here. What you want to do, if that's the case, click somewhere else and then use the arrow keys to get your purple cell, in this case, where it needs to go. Okay, so if you can't click directly onto the cell just because of the formatting that's going on, click somewhere else and then use the mouse key, the arrow keys, to get to that place, and then you hit enter, and now we have our z-scores calculated. Notice now that because our formula for z-score is taking all of the information from a single row, when we copy and paste it one row down, it still has access to all that correct information. And when we take that and copy it one row down and one row down and all the rows down, you can see, just double click on the cell, it is still accessing the correct information. We're still accessing the right mean, the right standard deviation, and the raw score that we want. So we can use that copy and paste feature to calculate those z-scores rather quickly. So we can do the one and then copy and paste that formula all the way down because we set up those three columns with the cascading waterfall of formulas and that parallel structure. All right, so we are just about to enter these z-scores into our answer cells. However, let's say that this was a situation where the answer cells were not there, such as on an exam. So on your exam, they're going to look much like these questions here, except you won't have the green grading cells. You won't have the green answer keys for your exam. So how can we test to make sure that we calculated these z-scores correctly? How can we gain a little bit of confidence to know, just double check that we used or we did the right calculation for the z-scores? Exactly. We can check the average and we can check the standard deviation, because the two things we know for sure about z-scores is that their average is equal to 0 and their standard deviation is equal to 1. So we can just very quickly calculate the average of the z-scores we just calculated, and we can very quickly calculate the standard deviation of the z-scores we just calculated. And the standard deviation, that's the easiest one to explain. I'll explain that first. The standard deviation is equal to 1. That's exactly what we want, right? So the standard deviation is equal to 1. We wanted a standard deviation of 1. That gives us confidence that we did this correctly. This number over here, that is scientific notation. And what that is that number is 1.776 times 10 to the power of minus 16. What that means is that this is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1776. All right, that's the number. That is our average. That's about as close to 0 as you're going to get in Excel. Okay, so that's what you're looking for. You might not get a nice clean 0, like we got a nice clean 1, but you're looking for that e to the minus something, right? And the higher the minus, the better. But even if you get like minus 4, minus 5, minus 6, that still means 0.0000 whatever. So that's as close to 0. So you are going to get some rounding errors because Excel doesn't have infinite numbers of decimal places. But that's what you're looking for. You're either looking for a clean 0 or for that e to the minus something. That gives us confidence that we did it correctly. So now let's pop it into the answer cells. And once again, because we use that parallel structure, we can copy and paste those answer cells all the way down. Until you're very confident with this, feel free to give it just a little double click to make sure that your answer cells are referencing where the answer actually is. We can scroll on down here and we can see that we have all the z-scores calculated correctly. All right, any questions on that calculation for the z-scores? All right, so the last thing we're going to do now is part B, which is the new standardized scores. So in this case, we've calculated our z-scores, And now we want to make a new distribution of scores. So we want to have a new distribution, transform these original scores into new standardized scores that have a very specific mean. We have a mean of 40, and it has a very specific standard deviation of 10. So the formula we're going to use is we are going to use the formula we're going to use is the one that we use to get a raw score from a z-score. So we are going to use raw score equals mean plus your z-score multiplied by your standard deviation. And the key hiccup that occurs to students when they're doing standardized scores is they forget where to find this information for the mean, and they forget where to find the information for the standard deviation, because they've already used a different mean and a different standard deviation previously in the question. So don't let that happen to you. When you're doing standardized scores, this is the new mean that you want. So in our case, this is 40. We want a new set of scores, and we want the mean of those scores to be 40. And we want a new standard deviation, and the question says, make that standard deviation equal to 10. So that's our new standard deviation. So make sure that you refer back to the question to get the numbers that you need for the standardized scores. So we're ready now. We can go here to a new column. We're going to call this stand X, just so that we know these are our standardized scores. And then we can just use the formula here. So because we're entering in these means from our question, we can just do that straight in here. So what I mean by that is you can put in equals 40. 40 is your new mean. And then plus, and then we choose our z-score, and we use Shift A to get the asterisk, and we're going to multiply that by 10. So this is 40, our new mean, plus your raw score multiplied by 10. And Excel will respect order of operations for addition and multiplications. So it will do the multiplication first, and then it'll do the addition. You don't need to put that into parentheses. So once again, we have our new mean of 40, and to that we're going to add our z-scores multiplied by the standard deviation. And then because we are, once again, accessing in our formula cells that are directly to the left of our formula, it's all in the same row, we can copy and paste that all the way down. And once again, as you kind of develop these skills, just give the copied and pasted cells a little double click, make sure they're accessing what you want them to access, accessing the correct z-score, 40 for the mean, 10 for the standard deviation. We're all good. So those are the standardized scores. So once again, let's say that you were in a, exam situation, and you were asked to calculate standardized scores that had a mean of 40 and a standard deviation of 10, and you calculate these new scores over here. What can you do to check to see if you've done that correctly? What can you do to check to make sure that nothing went horribly wrong? All right, I'll give you a hint. What was our mean for this distribution supposed to be? 40. So the mean is supposed to be 40. So if we did this correct, we should, when we calculate the mean of our distribution of our new scores, we should get a mean of 40. And lo and behold, we calculate the average, we have a mean of 40. What's the next thing we can double check? The standard deviation. We can double check that. It's supposed to be 10. And in fact, because we use these formulas over here, we can just copy and paste those to calculate the mean and standard deviation. And notice we have a mean of 40, we have a standard deviation of 10. So even before we enter these into the answer cells, we have confidence that we got those correct. So we can enter those in, and we copy them all down, and we see that we have those correct. So that's your z-score and your standardized score. And while I'm here, this is something that a few students have asked me before in terms of the number that Excel displays. So you can see here, we calculated our standardized scores and Excel was displaying up to 3 decimal places. But when we put these standardized scores into our answer cells, all of a sudden Excel is only displaying the whole number, no decimals. So three things to know about this. Number one, the numbers are still there. If you use the equals function, it doesn't matter what Excel displays. What it displays is not the number that's actually there. It has that number to, I don't know how many decimal places, but it only displays as many decimal places as the cell or the Excel sheet asks it to. So first thing to take comfort in is your number is there, right? So if you use the equals function, regardless of how many decimals are being displayed, all the decimals are still there. Second thing to know is that if you do want to see the decimals, you can take a look at them. So if you highlight your scores here, and then you go to up here to home, in the home sort of menu here, you'll see these 2 buttons here. These are what are used for increasing and decreasing decimals. So if you wanted to see more decimals, we can hit this button over here and just increase the decimals, and you can see that they're all there. If that's too many decimals, you can go the other way. If you want to bring some back, take some away. You want 7, you want only 4, whatever you want, you can make those decimals be displayed just in case you want to check those out. And then the last thing that this is a good point about is during your exam. The exam is a can you use Excel to do statistics exam, and not a sort of can you use Excel at a professional level exam. So that being said, what I mean is if anything goes weird in Excel, feel free to call me over, and if it's not a statistics issue, I will fix it for you. So let's say that you were doing your exam and you notice that your decimals aren't showing. Feel free to just put your hand up. I will come by during the exam and you can say to me, well, my decimals aren't showing, and I'll be more than happy to go here and be like, oh, there you go. Yeah, your decimals are there, no problem. Feel free if, this occurs. Let me see if I can get it. All right, feel free if this occurs and you just get those hashtags displayed in your answer cell, call me over and say, where's my number? I'll be more than happy to format it so that you can see your number. All right, so there's certain things in Excel that I will do for you because this is not a professional Excel course. However, if it is a statistics question, if you call me over and say something like, well, I typed in the formula for average here, I typed in equals mean, open parentheses, and Excel is doing this weird thing where it's going hashtag name, can you fix it? In that case, I will just let you know. I'm sorry, but that's a statistics question. You need to figure that out on your own. And in this case, the hashtag name is telling you that you gave Excel a formula that it doesn't recognize. So again, feel free, call me over if anything goes weird during the exam. If it's an Excel issue, I'll fix it. No questions asked. Don't waste your time trying to figure out how to do that. If it's a statistics issue, I'll let you know. And at the very least, you know that it's something that you should be able to fix. All right, so there are additional questions here to help you practice how to calculate z-scores, how to calculate standard scores for this. So let's wrap up our look today at z-scores by just a few kind of quick announcements about the upcoming homework. So we've done the practice. I would highly recommend complete that practice. You will get questions that look very much like that on the exam where I'm asking you to calculate z-scores, calculate standardized scores. So practice that cascading waterfall of formulas, practice that parallel structure. And then you are now ready for homework assignment number 5, part 3. This is an Excel sheet. This is not in my stat lab. This is only in Canvas. So this is in an Excel sheet that was uploaded to Canvas. It's in the Canvas files. complete it, you will re-upload it to Canvas assignments when you're done. And this is actually kind of good practice for the exam because that's also how you're going to submit your exam. So make sure that you do this assignment. Get comfortable with re-uploading completed Excel sheets to Canvas because that's also what you're going to do on your exam. But just so that you know, this is not in MyLab. I should get rid of that little MyStatLab thing. This is not in MyStatLab. This is available in Excel. It's a downloaded Excel sheet. It is automatically graded, so you have unlimited attempts to get this correct. So work on it, and then it'll automatically grade each question. It'll tell you what's correct and what you haven't gotten correct yet. And feel free to do it over and over again until you get the grade that you're satisfied with. Importantly, we are going to use sample variance and sample standard deviation for this assignment, so make sure that you're doing that. Everything in the assignment talks about samples, so make sure that you are using the correct formulas for variance and standard deviation. Post-test coming up due, so Chapter 2 post-test, that is due by February 10th by midnight. And then also, if you are taking advantage of the MyStatLab study plan, if you're earning mastery points to substitute in for your pre-test scores, the deadline to earn those mastery points is midnight before the day of the exam. So in about a week's time, try to finish up those mastery points. What I will do is the day of the exam, I will download your mastery points, and then whatever is higher, your pre-test or your mastery points, that will be your final score for each particular pre-test. So Chapter 1 mastery points due February 10th by midnight. Chapter 2 mastery points also due February 10th by midnight. All right, so we have just under 10 minutes left for practice time. So if you want to try maybe one of the Excel practice problems on your own, feel free to do that. Call me over if there's any issues. If you're all statsed out, feel free to call it an early day. And that is all that I wanted to cover for today.